In this video, I want to examine some of the basic vector notation and how to represent vectors algebraically. To begin with, most textbooks represent vectors using boldface letters. So for example, if we had a vector A, they'd represent it using this like a bold A. In this Paint program, it's difficult to draw bold letters, so I'll be representing vectors using an arrow. And the arrow will signify that this quantity A is not a scalar but is a vector. Now, say that we want to represent this vector algebraically. Say that we have this guy here. It's a vector in this direction, and we want to represent it in terms of numbers. How can we quantify this? Well, let's start off by first of all defining a coordinate system around it. So let's call this guy x, this guy y. Alright, now we know from vector addition that the parallelogram law will say that any vector, the sum of the vectors follows the tip-to-tail construction for addition. So therefore, we can see that, say that we want to try to construct this vector in terms of components. One vector along the x-axis and one along the y. Can we do that? Well, yeah. If we say we have this vector here, and then we have this vector here along the y-axis, so we just move it over here, then you can see that we can, from tip to tail, we form our vector here, let's call it A, just from these two components. And now that's where this component method of representing these vectors come in. And this is represented, say if we have an n-dimensional vector, we represent it as A1, A2, A3, all the way to AN. Now this is highly useful because now we've quantified this vector in terms of these constituent kind of like basis vectors. Again, a basis vector, we won't get into this too much because there's a lot of deep linear algebra associated with determining basis vectors, but for our purposes, these coordinate axes, our standard x, y, z coordinate axes, are basis vectors because we can represent any point in two-dimensional space using x and y. And we can represent any point in 3D space using the x, y, and z components. Therefore, this vector here, represented by these components, is uniquely defined in n-dimensional space. Therefore, using this component notation, we can write any vector in terms of these components of the coordinate axes. And one final way of representing this is in terms of actual unit vectors that are along these axes. So typically in the literature, the unit vector along the x-axis will be called I, and there's a hat put over it to signify that it's a unit vector. And this vector here, the unit vector in the y direction, will be called j, and again there's a hat. And now what this allows you to do is to represent, again with these components here, you can represent this vector A as a sum of these. Essentially these are the coefficients for I and j to produce A. In other words, say that our vector here is, for example, say that it was 2 and 3, and that was the component. And let's actually draw another example here. Okay, so we have our vector 2 and 3, 2, 3, and so that means that essentially we go 2 over here and then 3 up here. We kind of get something that looks like that. And now we want to represent it in terms of these vectors here, I and j. How do we do that? Well, again, we have I, we multiply it by 2, and then we get this vector here, and then we have j, we multiply it by 3, we get this vector here, and when we add those two together, then when we get our total vector. So we can write, say this is, we'll call it v, write v equals I hat times 2 plus j hat times 3 times. And this allows us to, again, decompose this vector v into these components I and j. And then from that, we can write it into this component form where we have 2 and 3, which represent these coefficients for our basis vectors inside the coordinate frame. So these are a few different ways of, again, we'll be representing vectors using the arrow. Now we can take a vector and make a coordinate system around it, and then represent that vector in terms of components of those coordinate axes. And that gives us this way of producing that vector through kind of a sum of these basis vectors multiplied by the components. And so this is, again, the notation that we'll be using and how to represent vectors in some different forms.